Hi everyone, allow me please in this video to share a little bit more information about one of the components in the space-time antenna which is very interesting. These components are the three nested spherical shells. What we know about them? Did ever Bashar mention something about this? Did he give us extra information about this? In my own research for the last 3 years, I find out that he's talking about this, not directly related to the space-time antenna, but he explained that the idea of nested capacitors is some kind of circuit itself which we do not yet have discovered in our planet. And this is very interesting because this can lead to innovation. And I would like to share with you a very small recording, audio recording, when he's talking about this, and then we will see how we can relate other type of information and we can discuss it. And here is the recording.
And in controlling it, do we change the physical length of the wire to tune it, or can I just use a reactant circuit to do that? Like a capacitor resistor circuit?
You can use that if you wish, but you will have to find a new design other than the ones that exist on your planet at this time. And we have already actually described this as a series of nested capacitors of certain volume and certain shape that create certain resonant frequencies within one the other.
That's in one of the other transmissions?
Yes, it is.
Nested capacitors, that's really interesting.
Yes, it is.
Because the space-time resonator is a nested coil, isn't it?
Yes, it is.
It's starting to make sense.
Thank you. It's about time.
We're kind of thick at this point in our track.
No, that's all right. I wasn't making a reference to that. I was giving you more information. It's about time.
Oh, it's about time and frequency.
Yes.
Interesting.
So now, as you can see in this recording, he's talking about time. He's talking about different frequency that they correspond, these nested capacitors. So we're going to see in this video how actually a sphere is relative or related to a frequency, how we can find the frequency of a sphere very easy. But also you see that he's talking about this idea in other transmissions. I do not know what is the name of this other transmission, but it happens that I have a small segment recording in my library, and I would like also to share it with you very few seconds, and just to see what he's talking about. And in this recording he is talking about alternative sources of energy, and that one of the idea to approach these alternative sources of energy is to use nested capacitors in a precise mathematical fractal ratios. Let's listen again, a very small part of this recording, and then summarize everything.
But you have to start thinking in a different way. You have to start looking at whole systems instead of components. You need to start understanding everything as one whole system so that you can see the balances, the currents, the flows that exist, the exchanges that exist on the various levels in nature, so that you can take advantage of those different levels of exchange and convert those different levels and transfer of energy from one level to another into energy that you can use. There are a variety of ways to do this. One of the ways would be to allow yourself to create what we might, by using your language, refer to as a series of nested capacitors. By creating certain capacitors of certain volume and certain proportion in what you would call mathematically fractal ratios, and nesting these capacitors within one another and then immersing those capacitors within certain mediums, you would find that each capacitor on a different scale would pick up certain frequencies within that medium and then release that energy in a certain way, going through the different nested capacitors to transform it in ways that are usable for you. That is one approach you can take. We are not allowed to help you all too much with this because it's up to your own process and your own imagination to figure out the details. But we can give you hints, we can point in directions. We are allowed to do that.
He's talking about these nested capacitors. He's talking about nested capacitors in a way that it will allow us to tap different levels, different frequencies. They need to be in a fractal mathematical ratios. So in our case, in the space-time antenna, those three spheres, they are in the golden proportion. The first one is 50 centimeters, the second one is 80 centimeters, and the third one is 130 centimeters. Those are Fibonacci numbers, and the relationship between them is with a golden proportion, or phi, or 1.618 times. Each one is bigger than the other. Now, in this video, we're going to talk mainly about three different things: how the frequency relates to a sphere, how a fractal relates to expansion and contraction, and also to the spheres. And also we're going to talk about capacitance, because he said that they are nested capacitors in series. And you know that when you connect batteries in a series or capacitors in a series, you increase the voltage. Now, let's start from the first one. How we can discover the resonant frequency of a sphere, the most easy way? Well, it will be different, it depends on the material, of the substance of the sphere, but generally speaking, the shape of the sphere. If it's, let's say, if we know what is the diameter of the sphere, we can multiply this diameter to pi, or 3.14, and thus then we can find the circumference. Once we know the circumference of the sphere, we can find the frequency. How? By dividing the speed of light, which is 300,000 kilometers per second, to the circumference of the sphere, and we're going to have the frequency. Let's give you an example to simplify this, to make it very simple. We're going to use a sphere that you are very familiar, and we're going to use also the resonant frequency, which you are very familiar. This sphere we're going to use here, it's our planet, Earth, because you know very well that the circumference of our planet is 40,000 kilometers. Now, you know that the speed of light is 300,000 kilometers. When you divide 300,000, the speed of light, by the circumference, which is 40,000, you're going to end up with 7.5 Hertz frequency. And ta-da! This is the Schumann resonance. So this is one way to find out the resonant frequency, but again, depends on what material is in the sphere. It may be a little bit different. In our case, if you do the math, if you multiply, I mentioned with you the diameters, but if you multiply this and you find the circumference, and then if you do the math, you will find out that approximately the bigger sphere, in our case, it's going to be about maybe 70 something megahertz, and the smaller one, which is half meter in diameter, it's going to be about 200 megahertz. We do not have the right equipment neither to send this signal, neither to register this signal at that time, but I'm sharing this with you because maybe we're going to have different resonant frequency in the higher frequency range. Usually when you have a resonance, it's not only one, sometimes 2, 3, 4, or 5 resonant frequency you can find. And because of this dimension, we may have different resonant frequency of this space-time antenna, but it will be so high that we could not register with the equipment we have right now. Now, let's talk about the mathematical fractal expression. Why these nested capacitors has to be with these fractal expressions. Now, in our case, I said that the spheres are also with a golden proportion between each other. Each one of them is 1.618 times bigger than the other. And this is the golden ratio. This is a phi. But this golden ratio actually it's a fractal expression. And let me give you an example to see why. The definition of fractal It's a pattern, geometrical pattern, which expand or contract, increase in size, in other words, or decrease in size, but it keeps the proportion, it keeps the ratio between each other. For example, this is the Sierpinski gasket, a fractal. You can see that triangles, it's always triangles. This one is bigger, this one is smaller, then it gets even smaller, but the relationship, all of them, they have 60-degree angles, so they are the same shape, the same pattern, but decrease or increase, and it changes the size. So this is a fractal. If you take 1 meter line and you call it A, and then if you expand it 1.618 times and you call this expansion B, then you're going to have a total length of 2.618, and we can call this C. And then you can see that B is 1.618 times bigger than A, but also the C, or the total line, is 1.618 times bigger than B. In other words, the ratio is the same, but the size is different. So when we're talking about fractals and spheres, we see that we can talk about contraction, we can talk about expansion, and the fractals are in a sense very efficient way to create contraction and expansion and to keep the ratio. So when we're talking about contraction and expansion and using fractals, this is very convenient, very efficient way to do that. And also you will see later on that when we're talking about an expansion, it will relate to kinetic energy, because the bigger the sphere, the higher it will be the circumference, and it will be a higher speed. So the higher the speed, it's more kinetic energy. The expansion will relate always to acceleration, to a higher speed, to more kinetic energy, and vice versa. The contraction, it will relate to deceleration, to lower speed, to more density, to more potential energy, or more time field. So these spheres, they act like, in a sense, a way to contract or to expand energies, to expand it outward and to contract it inward. And this is the other idea. The third idea is that the idea of capacitance. He say that they are nested capacitors. So what is capacitor? I'm sure that 99% of you know what is capacitor, but maybe some of you who watch this video do not know about what is this. So the capacitor is electrical component which is designed to store energy in a form of electric field, or to be even more precise, in the form of the potential difference between electrical charges. So in order the capacitor to store this energy, like electric field, it needs to have 3 different conditions. Usually the capacitor, in our case, is going to look like, in our reality, is looking like 2 parallel plates which are conductive, and they have non-conductive material in between, which we call dielectric material, and which can be made out of different things. But in our reality, the capacitors, the plate A and plate B, they have the same area always. They are 2-dimensional, they are flat. Okay, we can roll it and to put them in the cylinder, but they are basically 2 flat plates which have the same area. And the ability of the capacitor to store more energy, more electric field, it depends of this area. The bigger the area of those conductive plates, the more energy can store. And also the second condition is to have a lower gap, lower distance between those 2 plates. The smaller the gap, the higher the capacitance, or the ability to store more energy. And the third one is this substance in between, which is non-conductive. It can be air, it can be glass or plastic. If we change this substance, we can increase or decrease the capacitance of the capacitor, or the ability to store more charge, more energy. So just I want to give you a reference that in our case, in our reality, capacitor is usually with two plates and they have the same area, always they have the same area. But in the space-time antenna, we have dimensions, we have more dimensions, not two-dimensional flat plates. They have three-dimensional spheres. They have depth, they have width, they have height. It's multi-dimensional, let's say. They have volume. And not only they have volume, but also the bigger sphere, which is, if you do the math, it's going to be about 5.3 square meters, the area. It will be, the medium one, it will be about 2 square meters area. So you see that they will be acting, because they have dielectric, they have air in between, they will act like capacitors. You know, they're conductive, they're made out of copper, so they will act like a capacitor. But one of them, it's going to be approximately 2.618 times smaller than the other. This number, it's square of pi, or square of the golden ratio. In other words, if you multiply 1.168 or phi by itself, you're going to have 2.618. This is the relationship. If the spheres are exactly in the golden proportions, the smaller one will diminish or will shrink in the area with exactly square of pi, or square of the golden ratio. But simply it will be smaller. It won't be the same, like in our case with the conventional capacitor. So what will happen if we deposit 1 billion electrons on the bigger sphere? Those 1 billion electrons are negative, and they will create the opposite effect to the adjacent plate, in our case the medium sphere. But if they create the same force but with opposite charge, with positive charge, this charge will be distributed in the smaller area, and thus then we'll have higher density. Okay, so we increase the density. This is what happens. And this medium sphere will create again different charge, the opposing charge in the smaller sphere. In this case, the smaller will become negative, but again we will have a smaller area. We're going to have even higher density for this charge, where it can be distributed. And then we have the Merkaba inside. You know, the Merkaba is not touching the smaller sphere. Maybe you don't know that, but there is a spark gap in between, which is very, very small. And if you make the math, you will see that the Merkaba, it's made out of 32 triangles, and each one of them, they have a specific area. And if you combine this area, you will have 1.618 times smaller area than the smaller sphere. You're going to have again the golden ratio, golden proportions. So the idea is that these spheres, they are like our capacitors, but each plate have different area. In other words, the capacitance, it will be not the same. It will like shrink in a sense, it will diminish in a sense, but also there is something else. Not only they have different areas, but the distance between them is different. The distance between the smaller sphere and the medium sphere, in our case, it's 15 centimeters. Okay, and the distance between the medium sphere and the bigger sphere, it's 25 centimeters. So as we mentioned before, the smaller the distance, the higher is the capacitance, or the ability to store more charge, more electric field. The bigger the distance, it's less ability to do that. So you see that not only the area here is shrinking and the charge is more, let's say, compressed to have higher density, but also the distance between the shells, it's shrinking, and increase the ability for more capacitance. So we can say that towards the center, the capacitance, maybe it will increase, and towards the circumference, the bigger we make it, it will decrease in a sense. So what will happen if we connect battery in series, or if we connect capacitors in series? We will increase the voltage. Okay, the voltage will increase. The voltage is the potential difference. So the potential difference will increase. And when we have the bigger sphere minus, if we charge it with minus, then the medium is plus, the smaller it's minus, the Merkaba is plus. So this is like a series of nested capacitors. It must increase the voltage, you know, or the potential difference towards the center from my calculations. So there are many different also perspectives from where we can see this. I'm sharing just some of my discoveries. Maybe you can see it in a different perspective, and you can share your own point of view, which I'm going to be very curious to see what you think about this idea. But the main idea here is that those spherical shells, or those spherical or those nested capacitors, they have different volumes, they have different area, and this will lead, of course, to different effects, most probably to increase the voltage or the potential difference towards the center, to increase this compression towards the center, because we have a smaller area, and if the charge is again distributed in a smaller area, we have more density. So the idea is something that it's worth it, our exploration, because we may find something very innovative here with this idea. As Bashar said, you don't yet have it on your planet. And basically this is it. The fractals, they relate to expansion and contraction, because they're keeping the same ratio but different size. The capacitance also, it's very interesting relationship, and also the frequency, different size correspond to a different frequency. Once we know the circumference, we can find out the frequency of a sphere. So this is the main thing about these spheres. There are also other, let's say, approaches when we can see. Next video we're going to talk about them in a different way, how they reflect the signal, how they refract the signal, how they compress the signal together with the Merkaba, how they serve as reflectors, and what other functions also they serve. But in this video we saw them like a fractal expressions, we saw them like a capacitor, which is completely different from what we know, and also we saw them like different separate antennas vibrating in a different frequency, and thus then creating different effects. So this is going to be only for this video. In the next video we're going to see actually this Merkaba inside, what is the role and how it's interacting with these spheres, and we're going to talk more about the antennas and the energy gain, and different topics like that. So thank you very much for watching. I'm very happy that you are interested in these topics, and I can't wait to see you in the next video. Perhaps I will make it tomorrow. See you, and have a good day.